Quadrotor flips and tight aerial maneuvers are a benchmark for control of the system. In class, we've seen control schemes use things such as differential flatness and MPC to achieve impressive results. We wanted to see if we could do something simpler and perform flips through a decoupling of translational control and rotation.
We start by discussing the model for the quadrotor. The quadrotor has 4 propellers, each of which generates a thrust along the body's z-axis. These thrusts, as well as effects such as rotor drag, generate a torque about the center of mass of the vehicle. Using the Newton-Euler equations, we can derive dynamics for the quadrotor in terms of the total propeller thrust and the net torque about the center of mass. Notably, we have full and independent control of the overall thrust and the torque. The goal of this project is to explore what we can accomplish by exploiting this independence. We first develop an attitude controller to follow a desired angular velocity. Since the torque is fully actuated, we simply rearrange the rotational dynamics and apply first-order feedback control on the air, guaranteeing exponential stability to the desired angular velocity. Now, suppose we have a desired COM trajectory for the quadrotor. How can we design a controller to track this trajectory? Since we have high gain control over the rotational dynamics, we assume that we can command our thrust to point in any direction necessary. Then, we apply feedback control to drive the total tracking error to 0 over time. Assuming our rotational dynamics do converge quickly, this trajectory tracking will be stable.
We then implement a simple air drag model to see how the system performs under perturbation. Here, drag force is simulated in relation to relative velocity and orientation of the quadrotor with respect to wind direction. For the purposes of drag calculation, we simplify the quadrotor to be modeled as a flat square plane. Here's an example of the quadrotor performing a lemon skate trajectory in the xy plane. We saw that performance was quick to converge to a steady state and was similar across aerodynamic conditions, but could not be guaranteed to reach zero error. We evaluated this controller on wind speeds in the x direction ranging from 3 meters per second, or a light breeze, all the way up to 30 meters per second, which is a violent storm on the Beaufort wind scale. Specifically, because of the high gain of our system, trajectories were seen to perform roughly similarly with and without air resistance and across our range of winds, without control input ever exceeding 2 newtons of thrust per rotor. However, steady-state error did occur, and the system would not converge on zero error.
Next, we turn our attention to aerial acrobatics with the quadrotor. We define a flip to be a trajectory in which the quadrotor makes a full rotation about some specified axis. We want to be able to efficiently plan flip trajectories. To do this, we again decouple rotational and translational dynamics. First, we plan the rotational trajectory by performing direct transcription of the angular acceleration along the flip axis. The constraints are based on simple kinematics, and we wish to match some desired angular velocity. This is a convex quadratic program that can be optimized efficiently. Once we have our angular accelerations, we formulate similar kinematic equations for the COM position over time, based on the thrust applied at each time step. We can pre-compute the weights in each constraint, yielding another convex quadratic program optimizing the tracking of the COM to some desired flip trajectory.
Here's the quadrotor performing a circle and a lemon skate in a vertical plane corresponding to x equals y. We observed that this controller was rather sensitive to aerodynamic effects. Even by just incorporating drag effects without wind, the system was seen to drift from the goal trajectory over time without recovery. We also subjected the quadrotor to light air with wind speeds of 1 meter per second, and we saw that wind blowing in the plane of the flip was much more recoverable than wind blowing perpendicular to the plane of the flip. This is most likely due to the system having more control authority over error in the plane of its trajectory. There are some key limitations to our system. Although we can track trajectories while flipping, we currently cannot do flips of a specific size. These big flips require prescribing a trajectory in the roll or pitch of the quadrotor frame, but we only currently command the center of mass position, which we specified with a specific angular velocity. In this way, we can't optimize over time and allow for varying velocities that instead achieve a desired roll or pitch trajectory. As we just saw, flipping is also very susceptible to aerodynamic effects, something that could be countered with a lumped parameter estimation, or MPC. Flipping is also currently constrained to a single plane to allow us to optimize over a scalar rather than the space of 3D rotations. Finally, for flips, we are currently not minimizing control input and allowed for rather high thrust limits to achieve the aggressive maneuvers.